In a fluid mechanics class as a chemical engineer, you're going to need to be able to tell somebody what the height of a fluid is in a reactor that must be causing you to get some kind of volumetric flow rate exiting a valve you have just opened. And in a little bit more technical terms, what this is referred to as orifice discharging. And so what we're going to be able to do at the end of this video is be able to, given certain parameters such as a volumetric flow rate and the diameter of a valve, we're going to be able to tell you what the height of water must be in a vessel to generate these conditions. And this would be helpful if you wanted to be able to model the height of fluid in your reactor if all you had to go on was a mass flow or volumetric flow meter downstream. And so the very important equation that we're going to be working with is called the orifice discharge equation, and it is equivalent to Q dot, which is the volumetric flow rate, times something called C, which is the orifice discharge coefficient, times an area, times the square root of 2 times the gravitational constant times the height of fluid. And this height of fluid is H here, which is the level of fluid above the actual orifice in your vessel. And another important thing to note here about this orifice coefficient C is that these numbers are typically about 1. It's never going to be greater than 1, but it's also not generally going to be about 0. So you're looking at values between 0 and 1. The closer it is to 0 indicates that you have more frictional losses present. So if we were using pipes that had lots of surface area causing the fluid molecules to shear against the walls, generating lots of friction, we would expect to have a lower C value because intuitively we would expect to have a lower flow rate given more resistance through our orifice. And so with that out of the way, the next very important thing you're going to need to keep track of when you're solving these types of problems is dimensions. And the key with these dimensions and chemical engineering in general is making sure you have everything in SI units and you use the same units for everything. Now, when we were given our volumetric flow rate for our orifice, we were told it has units of 600 liters per minute. First of all, we don't use liters in these types of problems. We need to convert liters to cubic meters because we're going to be using G equals 9.8 meters per second squared. Height is going to have units of meters. Area is going to have units of square meters. And we will need Q to have units of cubic meters per second in order for the dimensions on both sides of this equation right here to actually make sense. Otherwise, we're going to get very incorrect answers. And so the way we're going to do this is we're going to look at Q, which has units of 600 liters per minute. And we will recall how there are 1,000 liters in 1 cubic meter of water. And what we're also going to do is say that in 1 minute, there are 60 seconds. And what we get from this is a volumetric flow rate that is equivalent to 0.01 cubic meters per second. And so this is good because now we have the dimensions equivalent on both sides of this equation that I'll call star for this video. And so the next thing we're going to do is evaluate the area. And the area is the area of the opening. We were told that the diameter was equal to 3 centimeters. So area for a circle is equal to pi r squared, which is also equivalent to pi d squared over 4, where d is your diameter. And what this ends up being, if we plug in the numbers and then convert everything back to meters, rather square meters, is 2.83 times 10 raised to the minus 3 square meters. And note how we are making sure we keep our dimensions consistent on both sides of our equation. Now with those two terms figured out, and because we were also given our coefficient, our discharge coefficient, which was 0.97, we can actually go ahead and evaluate this by algebraically rearranging it for height. And so doing that, we would divide both sides by CA, and we would square it, and then we would multiply it by 1 over 2g, and this would be equal to our height. And after we solve for this, what we would find is that our height would be approximately 0.64 meters. And so at the end of the day, what we have just determined is that at the instant our flow rate, our volumetric flow rate exiting this particular vessel, given this diameter opening, we can determine that the height of the water at that instant had to be 0.64 meters. So if you were designing some kind of height monitor, you could use your volumetric flow meter to calculate Q, and you would know your diameter a priori, and it would be a constant value. So you could very easily design some kind of process controller, like a PID controller, to regulate some kind of input into this system in order to keep things constant, to keep your volumetric flow rate exiting your reactor constant, or the height of water about some kind of value that you're interested in. And so that's going to wrap things up for this video. I hope you guys find it useful, and thanks for watching.